Again, because we are short of time, I started out writing the two basic equations that we had talked about before. Uh, you can all see the screen, right? And the equations.
Yes, sir.
Yeah, and you do remember that this was where we left the last class. We had discovered that in the two fluid model, after you make some approximations like the fact that rho and sigma, the density and the entropy density, they change very slightly. Okay? Then you end up with this set of equations. Actually, you end up with sigma square in the equations, but once again, sigma will really be sigma 0, the mean value, plus a small change. And because del 2 rho, Laplacian of rho only involves the changing part, right? When you take the Laplacian or when you're doing the time derivative, you only are talking about the part which is changing. The part which is constant, that of course does not contribute to either of this or this. So this is already first order of smallness in rho and change in rho, also in change in sigma. Because of that, the factor of sigma square which you have outside can be replaced by sigma 0 squared, where sigma 0 is the average value of sigma, the base value from which the fluctuation is happening, simply because terms like change in sigma times change Laplacian rho, these are very, very tiny. So we will not talk about these terms. Okay? I hope you remember the basic equation, although you may not remember all the details, but basically this is what the equations look like. And the major point here is that after all, we are looking for wave-like motion in a two-fluid situation. And of course, a wave-like motion usually would give rise to a wave equation. But the usual wave equation on any quantity looks like this. Second derivative of this quantity with respect to time, del 2 phi del t2, is proportional to the Laplacian of that quantity, with the constant of proportionality in front being the square of the speed of the wave. Okay? So usually you have del 2 phi del t2 is Laplacian phi into a constant. Here you have del 2 rho del t2 is Laplacian rho into a constant, but you have an additional term. Similarly, del 2 sigma del t2 has a Laplacian sigma into something, into this whole rho s by rho n sigma 0 square del t del sigma at constant rho. But in addition to that, you also have a del 2 Laplacian rho term. So what this tells you is that usually in a two-fluid model, density fluctuations and entropy fluctuations are actually linked to each other. So the Laplacian of rho essentially tells you, a term like Laplacian of rho would really tell you that if rho is not uniform in space, you're going to get a contribution from this. And that is equal to essentially the acceleration of rho, the second rate of change of rho with time. That is that signifies that fluctuations in rho act as a sort of restoring force, which tends to sort of move the fluctuation from one place to another. But here you see that not only are spatial variations of rho going to cause temporal changes in rho, even spatial changes in the entropy density may cause the thing to density to fluctuate with time, and vice versa. So the situation here is a bit more complicated than in usual waves. However, going by this kind of thing that you had for ordinary waves, what we are going to do is we are going to look at this coefficient, the coefficient which Laplacian rho has in del 2 del t2. Now, can anybody tell me what is the dimension of this? Del p del rho over sigma at constant sigma? Yes? Can of course work out the dimensions pretty easily. Del p del rho's dimension, whether you are doing the derivative at constant sigma or something else, only changes the actual function, but will not change the dimension. The dimension is delta p by delta rho's dimension, or pressure by density's dimension. So what is the dimension of pressure by density? Pressure is force, right? ml t to the minus 2 mass into acceleration per unit area. So L minus 2. And density is ml minus 3, right? So when you cancel all of this together, what do you get for the dimension? Yes? You have to say something because I need to know that I'm connected,
L square t to the power minus t2 inverse.
right? L squared to the minus 2. But what is that physical quantity then? That's a square of a velocity, right?
Yes, sir.
But that's obvious. Anyway, even if you had not done this calculation in full, you would have still should have known this because del 2 rho del T2, that's essentially rho by length square, and Laplacian rho, sorry, rho by time square, and this is rho by length square. So this factor has to be L square by T square. In fact, you can also see that from the fact that in the wave equation, the probability constant which sits in front of Laplacian of the quantity which is fluctuating has to be the speed of the wave squared. So this quantity has dimensions of velocity square. Similarly, what about this quantity? This quantity alone may have a complicated dimension, but note that this times this whole thing, rho s by rho n sigma 0 square. I can, of course, recalculate the whole dimension of this starting from the definition of temperature, entropy, and so on, but I don't really need to do that because I know that this is the coefficient of Laplacian sigma sitting in the expansion of del 2 sigma del T2. So rho s by rho n sigma 0 square del 2 del T del sigma at constant rho also has to have the dimension of velocity, right? And that is why what we are going to do is before we proceed any further, we are going to actually give them names. Del P del rho at constant sigma, this coefficient, I'm going to call U1 square, and this coefficient, rho s by rho n sigma 0 square, into del T del sigma at constant rho, I'm going to call U2 square. These are two velocities, at least dimensionally, U1 and U2 are velocities. What do they signify? That will come out from the calculation itself. But at least at this stage, we know that these are velocities, and in particular, if suppose sigma had not fluctuated, suppose sigma were constant for some reason, then this term would not have been there. Then this equation would have told you that density would fluctuate and the would travel like a wave, and the wave's velocity will simply be u1. So if you had no sigma fluctuation, you would have a wave with velocity u1. On the other hand, if you had no rho fluctuation, if this term had been zero, then this equation would have been an ordinary wave equation in sigma, and this would have been the velocity of that wave, right? So u1, u2, the quantities that we have introduced here, are basically the velocities that a purely density wave would have had or a purely entropy wave would have had. If the other quantity, entropy in the first case and density in the second, had been constant. Is that okay with everybody? Yes? Any questions about this? Okay, if not, let me just do one thing. In the two cases where sigma were zero, or not sigma were not zero, but sigma were constant, that's sigma zero, or rho was constant, whatever rho zero value, whatever average value it had, in those two cases, the wave-like propagation of rho in the one hand and sigma in the other case would be rather simple. But we want to analyze the motion of the whole thing given the set of equations like this. So how do we handle that? And the answer is that although the general solution to this equation could be very complicated, it's really not. not that difficult to figure out what kind of waves can propagate given that these are the equations. So what we will do is we will assume that you have a wave. Okay. So let me just do one thing. What I will do is, first of all, write this as u1 square. And here, this will become u2 square. This is a simplification that we have done. And then the next thing that I will do is I'm going to assume that rho and sigma travel like a wave in a particular direction, let's say in the z direction, and see what kind of speeds those waves can have. So I will assume for rho an equation like, note that rho just changes very slightly. So it changes about a mean value, and the change can have an amplitude of rho prime. And because I'm assuming that it moves like a wave in the z direction with a speed u, this is just the equation of a wave which is traveling in one dimension in the direction of in the z direction with a speed u. Right? I'm just going to assume that this is a solution to the equation and see what this tells us about the speed of such a wave. And similarly, at the same time, I'm going to assume sigma also fluctuates from its mean value sigma 0 with an amplitude sigma prime and a wave traveling in the same direction. So we are thinking of a simple situation where both the density and sigma, their variations, density and entropy variations travel along the z axis. And I'm trying to find out what kind of speed such a wave can have. Okay. Now, if I do this, let's look at what happens if I just take this and plug it into the first equation. Okay. So what will del 2 rho del T2 be if I were to differentiate this twice with respect to time? This term, of course, will not contribute. This is a constant in both space and time. This is just the average value. The contribution will only come from this term, right? So what will it give you? If you differentiate this once with respect to t, this term will come back with a I omega, right? As a factor. That's actually why we love using exponentials. Differentiation becomes very, very simple. What about del 2, del 2 rho, del T2? Just tell me what that's going to be here. Yes? Just differentiate this twice with such a t. No tricks involved. What will you get?
minus rho dash omega square e to the power
Yeah, minus omega square rho dash I omega t minus z by u. The rest. Okay. Now, what about this? You'll get u1 square. But now you have to realize you're taking Laplacian of rho. And what will Laplacian of rho give you? Laplacian is second. In this case, Laplacian, of course, is del 2 del x2 plus del 2 del y2 plus del 2 del z2. But in this case, it depends only on z. So you're basically doing two z derivatives. So what will you get from them?
z square by u square rho dash e to the power
Not z square by u square.
1 by u square. Sorry.
It's actually minus omega square by u square. I minus I omega by u. That's going to come down twice, right? Here I omega came down twice for two derivatives. Here I minus I omega by u came down twice, and minus I whole square being minus 1, you get this. Into, of course, rho prime, the I omega t minus z by u. That was the first term. What about the second term? The second term, let me just push the rest of the stuff even further below. For the second term, what you will have is this derivative del p del sigma at constant rho Okay, into Laplacian of sigma. But Laplacian of sigma also has a very similar behavior. It's going to be minus omega square by u square sigma prime into the I omega t minus z by u. Right? Is that okay? So now, many of these factors are actually common factors which you can cancel out. For example, minus omega square is there in every term. Drops out. This exponential is there in every term. They cancel out. Okay? And what you can actually do is multiply through by u square by u1 square, the whole thing, so that this u square also goes away. And then this becomes a minus u square by u1 square rho prime, which you can bring to the other side. If you do that, you're going to get this equation will become u square by u1 square from this minus, but you have moved it to the other side, minus 1 from this. I've just cancelled out the minus u square by u1 square term, rho prime. Plus basically the u square will cancel here, but there will be a 1 by over u1 square, which means in addition to this del p del sigma at constant rho sigma prime, there will be a 1 by u1 square, and 1 by u1 square, well, we already know what 1 by u1 square is, right? u1 square is del p del rho at constant sigma. So this is del rho is equal to 0. Okay? Clear? I've just taken this equation where I plugged the wave-like solutions into the equation here, and I've cancelled out all the common factors and rewritten the equation in this form. Is that okay with everybody?
Yes, sir.
Okay. Now, one more thing. This is first year thermodynamics in BSc. Do you remember what this kind of derivative is going to be? Del rho del p at constant sigma, del p del sigma at constant rho. Remember what this is? Nothing to do with specifically pressure or density or entropy density. I'm saying from basic maths which you learned when you did thermodynamics with partial derivatives, you learned one identity, I hope. I'm pretty sure all of you did this, which is if you have three quantities x, y, z, which depend on each other, so there is some function of x and y, let's say. If you have such a thing, then two things happen. First of all, del x del y at constant z times del y del x at constant z. Can anybody tell me what that is? These are partial derivatives being multiplied together. What is this quantity? Del x del y at constant z times del y del x at constant z. How much is this? Basic maths which you had learned definitely in first year when you did thermodynamics. Yes? This actually is very obvious, this one. One of the first things that you learn when you learn partial derivatives in the very first year is that partial derivatives are not always like ordinary derivatives. For example, things like del x del r and del r del x are not necessarily reciprocals of each other, right? But can you remember there, del x del r, when you're doing this, I'm talking of xy to r theta conversion. Del x del r is calculated at constant theta, and del r del x is actually calculated at constant y, right? This is why these two things are actually not reciprocals of each other, okay? Because the conditions are different. Here, however, you are saying that you are calculating del x del y and del y del x. with the same thing z being held constant. And here the result is very, very simple. Their product is simply 1. They're reciprocals of each other. Just like dy dx and dx dy are reciprocals of each other, for ordinary derivatives, partial derivatives actually are slightly different and you have to be more careful, but you have to also realize where the difference comes from. These two things are not reciprocal basically because they are evaluated under different conditions. But if you evaluate the derivatives under the same condition, in this case both z being constant, then these are actually reciprocals of each other. However, a more interesting thing happens when you multiply this. Why am I talking about this one? Because what we have here is exactly that. Note it's del P here, del P here, the same thing. They are del rho, del sigma, but at different conditions. These are constant rho, these are constant sigma. So del x, del y, del z at constant x into del z, del x at constant y. Anybody remember what this product is? Anybody? Okay, let me just tell you the answer, but you should really know this answer because after all, if you're going to give any of these competitive exams like NET, etc., you will need to know these results as well. These are elementary things for first year. This product actually happens to be -1. That's one of the first things you actually learn as a major difference between ordinary derivatives and partial derivatives. With ordinary derivatives, of course, dx dy into dy dx into dy dz into dz dx would have been 1, but this is not the case here. And note that, of course, these are at different conditions, z, x, y. So when you multiply these two things together, if you have to multiply this further with del sigma del rho at constant p, you will get -1. So this product is actually minus Okay, everybody clear about this? This part has nothing to do with superfluidity. This is age-old partial derivatives and basic property of thermodynamics. Okay. Now I will leave as an exercise the job of rewriting the second equation. That is, I've only stuck this solution, the wave-like solution, into the first equation so far. And I've got this. That the fluctuation amplitudes rho prime and sigma prime cannot be independent of each other. They have to be connected with this through this equation. Okay. Any questions? Okay, I will leave as an exercise the job of figuring out the other equation. I think I made a mistake there. Okay, I did make a mistake. I made a mistake in the sign. This should be plus. Although that will not change our final result, but still, this one will be plus. Because actually, when you put in the del 2 Laplacian sigma, you get a minus from here. So this term already had a minus, and therefore you actually end up with a plus in this case when you move everything to one side. And then the other equation, I'm just going to write down the answer for you. The other equation will actually give you this. I will not work this out for you, but it's essentially exactly the same thing. Just take this, plug it in here, and invoke the same amount, same old thermodynamics laws or partial derivative rules. Clear? So for the kind of wave-like motion that we have assumed, our wave equations essentially give you this: that rho prime and sigma prime have to be connected to each other via these two equations. Now, can anybody tell me what these two equations imply about you? The velocity of the velocity which is sitting here. These are two equations for rho and sigma prime, rho prime and sigma prime, right? Rho prime and sigma prime, the amplitudes of the waves, of the density wave and the entropy wave. Okay. So my question to you is, from these two equations, what can you say about rho prime and sigma prime? And for this, you don't even need to know a lot about the system. This is just basic maths. You have two linear equations in two variables, two linear homogeneous equations in two variables, right? Homogeneous because there are zeros on both sides. What are the possible solutions? After all, this is some matrix with these four numbers being the coefficients acting on rho prime sigma prime equal to 0, 0, right? So what's the solution for this? Yes? Isn't that? This is just a linear set of equations. So this can be written down as a 2 by 2 matrix with this as the entries, which I've just written as dots here. Acting on the column vector rho prime sigma prime gives you 0, 0. So what's the solution? Yes?
So u square by u1 square minus 1, then del rho del sigma.
M del rho del sigma what? What? What about that? Look, the most obvious solution to this equation is, well, staring you right in the face. If I call this matrix A and this is rho prime sigma prime, then rho prime sigma prime would simply be A inverse 0, 0, which is right. That's the obvious thing. The obvious solution would be rho prime is 0, sigma prime is 0. But that, of course, is not the solution we are looking for, because, after all, if it doesn't oscillate at all, then that's not a wave we are looking for, right? Rho prime equal to 0, sigma prime equal to 0 would tell you that the wave has 0 amplitude. The density wave and the entropy wave has no amplitude whatsoever. Isn't that? So the only possible way in which this can give you a non-trivial wave, that is a wave where you have fluctuating values of rho prime and sigma prime, is simply this. The only way that can happen is if the determinant of this matrix A vanished, which means if you had u square by u1 square minus 1 into u square by u2 square minus 1 minus the product of the two, or equal to 0, or these two things equal to. Okay? So So that's the only way there can be a wave if this condition were obeyed, and that means that there's only one possible speed for the wave, or actually two possible speeds because this is a quadratic equation for u square, so you should get two possible roots. Clear? So clearly two kinds of possible wave motion with two different speeds from the quadratic equation. Is that clear now? If this condition were not valid, then the only possible solution would be rho prime equal to 0, sigma prime equal to 0, which means no wave at all. This allows you to have a wave. Yeah? Tell me, is this clear or not?
Yes, sir.
But now we need to know a bit of thermodynamics to handle what this quantity is. Okay, I will not waste time doing the thermodynamics here. You should be able to figure this out yourself. Remember, sigma is the entropy density. So, just as a hint, T del S del sigma del T at constant rho. What will this be? Can you tell me what this is? Del sigma del T at constant rho times the temperature. What is this quantity? T del sigma, that's actually nothing but a heat, right? T times change in entropy. You differentiate that with the temperature, T del sigma del T. What you get is the heat capacity. And heat capacity at constant density means, of course, heat capacity at constant volume. This is basically CV. T del sigma del T at constant pressure is Cp. Now I will let you to worry about the thermodynamics you know using this, and you should be able to show that this is really this quantity. Something pretty familiar from elementary thermodynamics once again. Basically, the difference in heat capacity, the fractional difference in heat capacity, Cp minus Cv by Cp. Okay, that's thermodynamics. That's nothing to do with superfluidity. That's pretty straightforward old stuff. Now, the next step that we are going to use is basically this will tell us, this will give a quadratic equation. Two of its roots will give you two different kinds of possible wave motion. However, what we can always do is look at an approximation which is pretty nice here, pretty accurate for this particular system. Note that we are talking about waves in a fluid, right? In a liquid in particular, not in a gas. So in a liquid, can you say what kind of size this object will have? Cp minus Cv by Cp? The heat capacity at constant pressure and heat capacity at constant volume are not the same. They're different. But they're markedly different. They're basically different because when you heat something at constant pressure, the volume expands, the body expands in volume, and in the expansion, it has to do work against external pressure. So it takes more heat usually to heat something at constant pressure than at constant volume. Basically, because you need more energy to come in to give you the extra energy needed for the extra work done. However, that's because the thing expands as you heat it. Now, what kind of entity, what kind of object expands a lot when you heat it? If you heat a solid, does it expand a lot? Or a liquid or a vapor? Which quantity, which kind of state of matter expands a lot when you heat the thing up?
So gas.
Gas, right? Liquids or solids don't really do expand, but they don't really expand that much when you heat it. Which is why for liquids, which is a situation here, and for solids also, this quantity is very small and this ratio is nearly zero. Low expansivity. And because this is almost zero, you get a very obvious solution to this, right? If this thing is zero, at least approximately, then what kind of roots do you get for you? Your equation is simply u square by u1 square minus 1 into u square by u2 square minus 1 is approximately 0. So what are the two solutions possible? One solution that's possible is u equals u1, at least approximately. And the other solution that's possible is u approximately equal to u2, right? But now, the moment you have u fixed, these equations will actually tell you about possible values of rho prime, sigma prime. In fact, this gives you the ratio of rho prime and sigma prime. So if u is equal to u1, you see this term drops out. So this tells you the sigma prime has to be 0. So the first kind of wave that you have with the velocity u1, that's where rho prime is not equal to 0. You do have a density fluctuation, but you have sigma prime equal to 0. No entropy fluctuation. Density fluctuation without entropy fluctuation. Now, I'm not going to go back to the original equation and prove this for you. But if you look back at your notes in the last class, you will see that this will actually imply from the fundamental equations that if sigma prime is 0 and rho prime not equal to 0, that will tell you that there is no temperature gradient. And it will also tell you that Vn minus Vs vanishes. In other words, this is a kind of mode of vibration or mode of kind of wave motion where both the superfluid and the normal fluid travel with the same velocity. There is a density fluctuation. So normal and superfluid travel together. There is a density fluctuation, but no entropy fluctuation. Okay. So heat does not travel. It's just an object which the density which fluctuates from one point to the other. And this is the usual kind of wave which you see in all liquids. So this is, or all fluids actually. This is the standard sound wave in a fluid, and it's in this context, it's called first sound. First, simply because this is the first of the two kinds of sound that you can get for the two different kinds of velocities, two kinds of wave motion that you can get. Both are called sounds. First sound is like the ordinary sound where only density fluctuates. The second sound, well, this is the second sound, the sound with u2 as a speed. If you look at u2, u being equal to u2, that means this term would drop off, which means rho prime would have to be 0. So now you have a scenario where rho prime is 0, density does not fluctuate. That doesn't mean density is 0. Rho prime, remember, is the amplitude of density fluctuation. That is 0. But sigma prime is not 0. So there is an entropy fluctuation without a density fluctuation. And because there's no density fluctuation, this really means that there is no gradient in pressure. Pressure without this kind of wave occurs without a pressure gradient. And you can also show from the basic equation, I'm not going back there, but you can easily show this from the fact that density does not fluctuate. You go back to the equation of continuity, you should be able to show very easily that this is what you have. So there is no density current. So this is a very new kind of wave, a very different kind of wave, a wave in which there is no transfer of actual material from one place to another. Density does not change. Notice that this equation here tells you that the normal fluid and superfluid actually travel in opposite directions in such a way that there is no change in the density, overall density. And what happens on the other hand when normal fluid and superfluid travel in opposite directions? Superfluid carries no entropy with it, but normal fluid carries entropy with it. That is why entropy fluctuates. So here you have an entropy fluctuation, and as a result, a temperature gradient which is there in the system, but no density fluctuation. This is a very different kind of motion, which does wave motion, which does not happen in ordinary fluids at all. And this is what is called second sound. So second sound is a special kind of wave motion where only entropy fluctuation takes place. Normal and superfluids travel in opposite directions, maintaining the density at a constant value, but changing the entropy. Of course, this is an approximation because I'm assuming that Cp minus Cv is negligible compared to Cp. This is nearly zero. And we have already made small ambiguous approximations. If this approximation, if you want to look at a more precise version, then of course you would have to solve the quadratic equation here, and there you will see that the first sound is a sound with u close to u1. That will be almost no entropy fluctuation and rather large density fluctuation. And second sound will be almost no density fluctuation with a rather large entropy fluctuation. Okay. So this was the other last major topic that we wanted to discuss in superfluidity. Any questions about this?
No, sir.
Okay, so now that that's done, let's talk about superconductivity. That's my second topic. Of course, I should have actually started it on a different class, but I don't have many classes left, so I will have to talk about this quickly. I'm not going to discuss the phenomenology of superconductivity at all with you because I'm assuming that you have already studied that, right? London equation and stuff like that. In the previous class, things like Meissner effect, uh,
So,
the fact that you have critical magnetic fields and stuff like that, things you must have studied before, right? Haven't you?
yes, sir.
Okay, so I'm going to basically talk about BCS theory in this course. But before going to BCS theory, today I'm going to talk about something which I've already studied before, but maybe you have not done the full calculation, which is Cooper pairs and their basic theory. Now, the first point is, why do you need Cooper pairs? Now, you all know the basic phenomenology of superconductivity. Below a particular temperature, the critical temperature, a superconductor essentially behaves like a perfect conductor. And that is only possible if there's some kind of condensation which occurs. If the whole system, or at least a large fraction of the system, macroscopic part of the system, behaves like it's in a single quantum state. So basically, the idea, know that we started with bosons and condensation, then talked about superfluidity. Now we are talking of superconductivity, and there's a common thread in all of these. This should be a condensation phenomenon as well. Okay. Condensation in this case means that a macroscopically large number of particles should be in the same microscopic state, the ground state. But there is a major problem here. Bosons and condensation actually occurred with massive bosons. That was purely theoretical to begin with. Today we have real systems where you can see this. Superfluidity, the kind of superfluidity we were talking about was superfluidity in helium-4. And helium-4 was bosonic. But when you're talking of superconductivity, these entities which condense have to carry charge, right? After all, conduction is conduction of charge. So they have to be charged particles. And the kind of charged particles which carry current are well known, they're electrons. The trouble is electrons are fermions, right? They don't obey Bose-Einstein statistics. So they should not show condensation. That is uh, the basic problem here. So the solution to that is also something which you already know. That is what Cooper pairs are, which is although individual electrons cannot form condensates because they are not bosons, bound pairs of electrons can, under proper conditions, behave like bosons and hence can condense. After all, bound pairs of electrons have ultimately integer spin, right? Two spin halves together form integer spin particles. And essentially, if you are going to exchange a bound pair, you're exchanging two electrons. And the moment you exchange one bound pair with another, a pair of electrons get interchanged with another pair. And that means you get two minus signs and a plus sign in the wave function. So effectively like a boson. At least that's a loose way to understand that. But the problem is, okay, first of all, bound pairs of electrons can behave like bosons. But why should electrons form bound pairs at all? What is the problem here? Why can't electrons form bound pairs? Or why don't we expect electrons to form bound pairs? Yes? Why don't we expect electrons to form bound pairs? That should be easy to answer. Bound pairs can form between things which attract, right? And electrons are fermions. Not only fermions, they're both negatively charged. They should repel. So this is a basic problem. That why should a bound pair be at all formed? And it's even worse than that because we are in three dimensions here. And in three dimensions, we have a result which you must have studied in elementary quantum mechanics. If you have studied a 3D well, a well, of course, means an attractive potential causing a lowering of the potential energy. But a 3D well will have to have sufficient depth. That is, the strength of the potential must be large enough to form bound states, to enable bound states, basically. So, first of all, there's this puzzle. Why do electrons at all attract each other in 3D? After all, electrons being negatively charged should repel each other. That is the basic problem. The other issue is even if we somehow could cook up a situation where electrons attract with each other to each other, we wouldn't expect the attraction to be too large. But in three dimensions, as we know from the standard simple problem of three-dimensional potential well, unless the attraction is strong enough, you don't get a bound state at all. And contrast this with a one-dimensional case. In a one-dimensional potential well, again elementary quantum mechanics, you always have at least one bound state. You can have more than one, but you at least have one in a 1D well. In a 3D well, on the other hand, you may not have any bound states unless the depth of the well is sufficiently large. I don't know whether you remember these results, but I think these results should be standard knowledge for everybody. And if you don't remember them, you should look up your quantum mechanics book. But you can see that there is a bit of a big problem here. In order to explain superconductivity as a condensation phenomenon, you need the electrons to condense into a single macroscopic state. But electrons being fermions, they can't. However, bound states of electrons can behave like bosons, and so they can. The real problem is why should they form a bound state? They repel each other. Even if they, even if we can manage to find a mechanism by which they could be made to attract, even then the attraction would be usually rather weak. And weak attractions in three dimensions usually do not lead to bound states. So there are lots of problems in this whole scenario. But let's take them one by one. First of all, how do you expect electrons to attract each other at all in the first place? Two electrons in vacuum, can they attract each other? Yes? Is it possible for two electrons in vacuum to attract each other? Just hold on. Getting a call. Okay, so all of these are basically problems. Now, the solution to this, two electrons will not attract each other in a vacuum, but superconductivity does not happen in a vacuum. It happens in a solid. Right? At least the conventional superconductors are all solids, or at least near solids. So there is a solid lattice, and the basic idea here is the following. You have an ionic lattice in which, suppose an electron were to travel through it. What would happen in this case? The electron being negatively charged would attract the ions towards it. So the ions would sort of move from the equilibrium positions. The lattice would be distorted by the presence of this electron. Okay. Now this once the electron goes away from here and goes far away from this region. So the big lattice, of course, it has not perhaps left the solid, but it moved to a very far away region. What happens to this region? Do the ions stay distorted or do they go back to the original equilibrium position? Yes? What I'm saying is an electron came in here and then moved away to another part of the solid. So when it was here, it distorted the ions in the vicinity. Okay? But when it has moved far away, what happens to these ions? Do they stay in their distorted position or do they go back to the equilibrium position? What do you think happens? Yes?
So it goes back to original position.
Exactly. They should go back to their original position, but does that happen instantaneously? There is a moment the electron goes away, the ions go back. Does that happen? Do you expect that to happen? Remember, the ions are a lot heavier than the electron, right? As a result, their motions are a lot slower. In other words, the relaxation time, the typical time which the ions take to go back to the original position, that actually is pretty large compared to the time it takes the electron to move to an entirely different part of the solid. Okay. So what could happen in a scenario like this? The first electron has moved, gone through this, moved somewhere here, very far away. Another electron comes in here. Now, it is now moving in a distorted lattice where the positive charges are closer together than they usually would be, right? Closer to the electron than they usually would be. This will actually cause the electron's energy to go below what it usually would be. Because if you have positive charges which have come closer to it, its energy would drop, right?
Yes,
Is it
sir.
okay? So basically, this electron feels like there's an attractive potential because its energy has been lowered. And what has caused this attractive potential? Well, what has really caused this attractive potential is the fact that the lattice has been distorted and the restoration relaxation time of the lattice is so large that it stays distorted even after the other electron which caused the distortion that has gone away. But now you have a situation like this. The two electrons are very far away from each other. So their direct Coulomb repulsion is very, very weak. So the energy rise of which this electron would have felt because of the Coulomb repulsion, that is actually very small. But the energy drop that it feels because of the fact that the lattice has been distorted and the ions have not relaxed back completely, that is going to be rather large. So because of this interaction via the lattice, the electron effectively ends up lowering its energy compared to what it would have. So is the electron lattice electron interaction. So it's basically an electron-electron interaction effectively. It's like essentially this electron which is causing the energy of this electron to be lowered, but via the interaction with the lattice. So this electron lattice interaction, lattice electron interaction, or effective electron phonon interaction because of the lattice vibrations, that causes the lowering of the energy. Okay. So it's not two electrons directly interacting with each other. Direct interaction would only have raised the energy. But effectively, what can happen via this lattice distortion is that one electron can effectively attract the other electron. In other words, lower the energy of the other electron without directly coming in contact. You note that for this to work, the two electrons really have to be rather far away. So this electron should have moved quite a long distance away from this electron. Okay, clear? Yes?
Yes, sir.
So we have solved one part of the puzzle, which is how two electrons attract each other. They don't really attract each other directly, but they do it via distortion of the lattice. But the other question would be this effect would be rather small. So in 3 dimensions, we know that you need sufficiently strong interaction, strong large strength of interaction before you can form a bound state. But we need bound states. And this is where, rather contradictorily, the fact that electrons are fermions are coming here. The important thing is the electrons are moving, but they're not moving in free space. There are lots of other electrons around. And what is important is that almost all of the energy levels below the Fermi level, at absolute zero, all the energy levels below the Fermi level, but even at ordinary temperatures, almost all of them are actually filled up, right? So the result which follows, this is basically Cooper's theorem, which I'm going to prove via calculation, Schrodinger equation calculation the next day. Cooper's theorem essentially tells you that in the presence of a filled Fermi sea, This is important. So all levels below the Fermi level, all energy levels available below the Fermi level are actually filled up. In such a situation, here the attraction, of course, is the lattice mediated attraction. Then it's tiny. So this is Cooper's theorem, that if you have a field Fermi sea, then and only then would an arbitrarily small interaction between two electrons lead to a bound state of two electrons, lead to a Cooper pair. Okay? So have you done this theorem before, or this proof? Yes or no? You know that there are Cooper pairs, but the basic idea behind the formation of Cooper pairs is this theorem called Cooper's theorem, which says that this is something which would never have happened in free space. Even if you had managed to get somehow a situation where two electrons actually attracted each other, if the attraction was very weak, which is the case here, in free states in vacuum, two attracting electrons would never have formed a bound state. But because you have a filled Fermi sea and electrons are fermions, all levels below the Fermi sea are not available to the electrons. That somehow ends up giving you this result, that two electrons, even with a very weak attraction, can produce a bound state. So notice that this is a rather funny situation. We started by saying that electrons, being fermions, cannot form condensates directly. You need bound pairs to form condensates. How can you form bound pairs? You can form bound pairs only if there's an attraction. So using this electron lattice electron interaction picture, we can understand why two electrons can still be able to manage to attract each other. But even that kind of attraction would not have produced a bound state unless electrons were fermions. Because electrons are fermions, you have the Pauli exclusion principle, which means in a filled Fermi sea, all energy levels below the Fermi momentum are unavailable to form a wave function of the system. And in such a situation, you can prove that a bound state formation can occur. So this is a rather delicate scenario where, because electrons are fermions, you have a problem in the first place, and the solution to that lies in the fact that the electrons are fermions. Next day, we are going to prove Cooper's theorem. I'm assuming that you have not done a proof of Cooper's theorem before. Have you? If you have, then we can skip that and go on to the next topic. That is, which is BCS theory. But have you proven Cooper's theorem before? Yes?
No, sir.
Okay, so next day we'll start with Cooper's theorem. We should be able to finish that proof in less than one class, and then go on and start talking about BCS, the standard theory of superconductivity, at least not the so-called standard superconductors, not the high DC superconductors, but the ones before that. Okay, so let's call it a day today. Next day we are going to meet on Friday, this Friday, at 7. If you have any problems with that date, let me know when we know beforehand. But I think we will have to have more classes in a week, at least 2 classes every week for this week and the next, and maybe one more class after that to finish the whole thing. Okay? So
Okay,
let's
sir.
call it a day today.